Okay, so you can hear me, right? Okay. All right. Thank you so much. So first of all, thank you so much, Moitrio, for the wonderful introduction, and thank you for inviting me to talk here. And so yeah, first of all, a few disclaimers. So this is a joint work with Professor Indranil Biswas, Professor Chitrabhanu Chaudhuri, Ritwik Mukherjee, and Anantadulal Paul. Um, so this is part of my master's thesis, which I'm currently completing and the process of completing. Um, so yeah, the main disclaimers are that please do interrupt me whenever you feel like asking a question, or uh, if you have some comments. Um, it will be actually very helpful for me, because in that case I will feel like I'm not talking to my screen, but to actual people. And I'm also not sure of everyone's background, so I might say things which seem obvious to me, but they might not seem obvious to you at the moment, which might be because I spent some time with these things, so I might feel more obvious. But it could also be the case that I am saying something wrong, or I'm saying something which needs more justification. So the easy way to avoid this is to please interrupt me whenever you feel uncomfortable with anything. Right. Second disclaimer is I tend to write a lot of things in my slides, much more than is traditionally advised for. I don't know why I have this bad habit. I do. I'm trying to change it, but in these slides, that habit has not been changed. So I have written a lot more than is actually required. But so please don't be distracted by all the writing in the slides. I'll point to you the parts that are necessary for just the basic understanding. All right. So let us start. So I'll be talking about counting rational curves with a certain kind of singularity, which is known as an M-fold point. So by the way, whenever I say an M-fold point, I probably mean an ordinary M-fold point. I'm not sure about the terminology in algebraic geometry. I think M-fold point has two different meanings depending on how you look at it, but I'll explain in more detail what I'm talking about. Anyway, so here is the brief outline of the talk. So I'll start up with the main setup of my problem, the problem that we are considering here. I'll do some literature review of what has been done in this kind of problems, and then I'll state the main result that we come out with. Then I'll go to there will be part one of the talk. The part two will consist of the preliminaries of actually understanding that part. So this will probably constitute the major part of the talk. I don't want to go into very technical stuff just directly from our paper, and no one understands anything. I hope I'll try to start up from a decent background, and hopefully that will give you some idea of what is going on. If you have any questions, again, please stop me. And finally, I'll try to give you a brief idea of our work that we have done. I'll not definitely not go into the details. I'll try to give you the main idea depending on how much time I get. And yeah, I'll hopefully, if I get some time, I'll talk about some interesting future problems that we are also thinking about. All right, let's start. Um, so, so this broad field that I'm working in is known as enumerative geometry. So this is a subfield of algebraic geometry. Algebraic geometry um, studies solutions of sets of polynomials. So in one dimension, that's very easy, because for an algebraically closed field, any polynomial has finitely many zeros, finitely many solutions, and as many as its degree counted with multiplicity. But when you increase dimensions and when you increase the number of polynomials, these form very interesting structures. Some of them are smooth, some of them have singularities, and it's an interesting field of study, which is broadly known as algebraic geometry. Uh, right. So, as a subfield of algebraic geometry, there is enumerative geometry, which asks questions like what kind of or how many objects are there, how many geometric objects are there in a certain space that satisfies certain constraints. So these geometric objects often tend to be simple objects like curves in a certain space, which are defined by some polynomials, or they could be more exotic stuff like sheaves in Donaldson-Thomas theory. Anyway, the most basic example of such an enumerative question is, so for example, how many lines pass through two distinct points? It is probably not very surprising to know that this answer is 1. There is only one line passing through 2 points. But what is actually surprising is this is enough information to answer the following much more non-trivial question, which is that how many genus 0 curves are there in the projective plane which pass through 3D minus 1 generic points? Okay, I should have said how many genus 0 degree D curves are there in P2. Sorry about that. Passing through 3D minus 1 in the D is the degree of the curves. So this is a very classical question in algebraic enumerative geometry, and this was actually an open question for a very long time. But anyway, this particular question has eluded mathematicians for a long time. This is probably dates back to 100 years, I think. Yeah, so the most easy answers are, so let's ND be the required number. So what is ND? ND is the number of rational degree D curves or genus 0 degree D curves in P2 passing through appropriate number of points. And the numbers N1 and N2, which means number of lines passing through 2 points, or number of conics, as in degree 2 polynomials passing through 5 points. These numbers are 1. These have been known for a long time. In 1848, Steiner computed N3, which was number of cubics which have genus 0 passing through 8 points. And I think after some time, by 19th century, Zeuthen computed N4, and then by 1980s, N5 was computed. So you can see already a lot of time has passed since 1848 to 1980s, and we could only go up to N5. We had no idea about computing ND for all D, which means for any degree D curve, can we compute the number of rational degree D curves in P2. Now, this was far from reality, this computing ND for all D. So the breakthrough came in 1994, interestingly from ideas, interestingly using ideas from physics. So I'm sure a lot of you have heard about Maxim Kontsevich, and he had written a paper with Manin, in which he gave a recursive formula to compute this number ND for all D. For all degree D, he gave a recursive formula which was very explicit, very crystal clear. There was nothing ambiguous about it, and it gave you all the, yeah, that is true. That is a sad news. So that gave ND for all D, and what the main idea that was used was actually motivated by topological string theory and something known as the associativity of the quantum cohomology of P2. Anyway, I will not get into all of that stuff. Those are more technical stuff. But I'll try to, my main aim of today's talk will be to try to give some idea of how Kontsevich's recursion, the proof of Kontsevich's recursion works, at least in a geometric way. I'll try to motivate a bit of relations to physics, but I am not very knowledgeable along those lines. I'm very interested, but not very knowledgeable along those lines. So I won't be able to give you a lot of comments on that. Anyway, so the point that I was raising before, we all know that a recursion needs a base case to work, otherwise it's useless. So Kontsevich's recursion is extremely elegant in that sense, because the only base case that you need to solve that is the fact that N1 equals 1, which means that only one line can pass through two generic points. And this is what I was saying. This is the only information that you need to actually compute all ND for for ND for all D. And that is actually quite beautiful if you think about it, because if you just have the recursion, then I mean, I don't know if you feel that way, but just knowing that a very trivial information that only one line can pass through 2 points, you can actually compute the number of all degree D rational curves in P2, which was a very open question for a very long time. Anyway, so uh, as some of you might know, that Kontsevich was awarded the Fields Medal due to contributions in his work in this, and also for his proof of the Witten's conjecture. This was another long-standing conjecture in intersection theory. I should have written was awarded the Fields Medal. Sorry about that. Right. So, okay. So we understand the question of how many rational degree curves are there in P2. So by the way, when I say rational, I mean genus zero. All right. I'll explain what genus is in a moment in more detail, but for the moment, just bear with me. So, Kontsevich has answered the question how many rational degree curves are there in P2 very well, and it was completely understood, well understood. So after that, mathematicians started looking at the following type of questions, which is that, okay, we know how to count rational degree curves, but now what if I also add the constraint that those curves have certain singularities? So as I said, algebraic objects used in algebraic geometry have really exotic structures, and one of those exotic things is their singularities, which is not something that you find in smooth manifolds, for example. Smooth manifolds is everything is very smooth. I mean, smooth in the sense that it is actually smooth for the layman, and in a more technical sense that it has a smooth atlas, a smooth um, system of charts on it. But you cannot do that in for all algebraic varieties, for example, because you will have certain things known as points known as singularities, where you cannot have a chart around that point, which will uh, uh, result in well, you can then classify those singularities up to using various methods from algebraic geometry. So one type of question is that, okay, fine, suppose your curves have certain kind of singularities, then you ask the new question that, okay, how many degree rational curves are there in P2 that have a singularity of a certain type chi, and which pass through appropriate number of generic points. The passing through number of generic points, I think, is obvious, because if I mean, the reason for asking that is, I think, obvious, because if you ask the question, how many lines are there? Well, that makes no sense, because there are infinitely many lines. But if I say how many lines are there through one point, that also doesn't make sense, because there are infinitely many lines through one point. But what if I ask if there are how many lines are there through points, then you can say, okay, there is only one line through 2 points. So it is important to ask the right number, or give the right number of constraints to your curve, so that you can expect a finite number as opposed to something that is meaningless. Also, if you ask how many lines are there 3 points, if those points are not collinear, then you won't find any line going through them, so that will be 0. So that's too many constraints. And if you make them pass through only one point, that's too few constraints. So you have to find the exact right number of constraints. So this is what I mean when they say that these pass through appropriate number of generic points. Appropriate, so that you can expect a finite answer. That answer could be 0. That's a separate matter, but the answer should not be 0 for dimensional reasons. The answer should be 0 because there are actually no curves. Anyway, so this question has been studied extensively when the singularity is a triple point. So let me just tell you about what a triple point is. So I'll tell you what an M-fold point is, rather. So when I talk about an M-fold point, I mean an ordinary M-fold point. So so let's start with the two-fold point. What is a two-fold point? A two-fold point is a point in a curve which looks something like this. So this point is a two-fold point. What do I exactly mean by that? I mean that given that point, I can find a local chart around it in which this looks like the intersection of two lines, right? This is known as a two-fold point because intersection of two lines. That's the important part. What is a three-fold point? So by the way, this is a two-fold point, by the way, is also called a node. Okay. What is a three-fold point? Again, whenever I say a three-fold point, I mean an ordinary three-fold point. So a three-fold point would look something like this. I hope I'm drawing well enough. And if you look at this point, then, and if you take a local chart around it, then this will look like the intersection of, this is one line, this is two lines, this is three lines. So intersection of three lines, and so on. And you can keep playing this game. And of course, I'm drawing this in a real case, but I want to ask questions in complex over the complex fields where I cannot draw these things like this. That's that's not something that we can easily visualize. But for visualization in the real dimensional case, this is what you think about. This is how a two-fold or a three-fold point. So this is known as a triple point, by the way. Okay, so yeah, so this question was extensively studied for the case of a triple point, and there are lots of people who studied this: Sheldon Gatz, Ravi Vekil, Zivran, Alexis Ringer, and so on. And the interesting thing is that this problem was actually not solved beyond n greater than 3, because well, most of these things use something known, or most of these methods use something known as excess intersection theory, which is basically I should not go into that. Basically, you construct a moduli space on which you do intersection theory, but then what you actually count is more than what you actually want to count, because there are contributions from your boundary, and you want to subtract off those contributions to actually get the number that you want. And doing that is a very, very complicated process in many situations. So due to these situations, for n greater than 3, the situation becomes very, very ugly. So this question there was no explicit formula anywhere for the case of counting rational curves with an n-fold ordinary singular point. So given this context and this literature survey, I will now talk about the main result that we obtained. So as I said, in a joint work with Indranil Biswas, Chitrabhanu Chaudhuri, Ritwik Mukherjee, and Anantadulal Paul, we obtained this following result, which can be found in our preprint, which is that for any m greater than or equal to 3, where m is an integer, we have a recursive formula. We prove a recursive formula to compute the number of rational degree curves in CP2, passing through 3D plus 1 minus m points. Those are the correct number of points. That comes from a dimension counting. Don't have to worry about that right now. And which have an ordinary m-fold point. And the main idea behind our result was to pose this, well, I guess non-trivial question in a way that it makes it slightly less organic. So it's not the way that you would usually go thinking about it, but but we lose that organicity of that looking at the question. But we gain what we gain is that dealing with the question becomes much easier, which I'll tell you in a moment. Hopefully by the end of the talk, why exactly. And the way we do it is to use the already well understood idea of Kontsevich's recursion, and we extend it to some a fiber bundle versions. We extend it to a family version of the question. I'll explain what those things are. And we also use a certain correspondence, and Kontsevich's recursion, we obtain this formula. Okay, so this is the result that I'll hopefully reach to by the end of this talk. But for the major part of the talk, I'll be focusing on the idea of the proof of Kontsevich's recursion, because to understand our result, one needs to understand that properly. Okay, let's start with preliminaries. So I'll start with some basic stuff. So here is the part where you definitely should ask questions if you don't understand it. Okay, so what is a curve? A curve in P2, so when I say P2, I mean CP2. CP2 is complex projective plane, which is C3 minus 0 modded out by the C star action. In other words, you can think of it as the set space of all lines in C3. I hope you guys are comfortable with projective spaces. If you are not, then just think of a plane. It's not exactly a plane, but you can think of it. So a curve in P2 can be defined as the zero set of a homogeneous polynomial in 3 variables. And the reason we are talking about homogeneous polynomials as opposed to just polynomials is because we are in the projective space, and zeros won't be well defined unless we take a homogeneous polynomial. If you don't understand this comment, then please ignore it. So a curve in P2 is said to have a singularity at a point if all the partial derivatives of that polynomial vanish at that point. So what it basically means is that around that point, you do not have a smooth chart. So for people who are not comfortable with this, I'll just give you a think of how to think about it. So a singularity would be something like this, something around which the thing is not smooth, whereas this is a smooth point. This is a smooth point in a very vague sense, and this is a singular point. in a big sense. Of course, we want to make it mathematically precise. We have to talk about charts and etc. etc. So I won't go into that. But yeah, please feel free to ask if you have any questions. Okay. So so this has a singularity at a point if all the partial derivatives vanish, and we denote the set of all singularities of C to be sing C, and we call C to be non-singular or smooth if this set is empty. So which basically means that there are no singular points. Then it's a smooth curve. I hope this is fine. And using a very simple application of implicit function theorem, one can prove that any projective curve in P2 admits a holomorphic atlas outside of its singular point. So if you exclude its singular points, it will admit a holomorphic atlas. What do I mean by holomorphic atlas? There will be a system of charts such that your transition functions will be holomorphic. I hope you understand that. If you don't, then, well, outside singular points, your curve is smooth in a big sense. Okay, so it is a very well-known result that, well, actually, what I'm right now saying is directly follows from the previous result, which is that if you have a non-singular projective curve in P2, then it is nothing but a connected compact Riemann surface. What is a Riemann surface? A Riemann surface is a surface with a complex structure on it, which means you have a system of charts such that the transition functions are holomorphic. And if you don't understand that, then well, think of it in a way that you know the complex plane, and you know how you can make sense of holomorphic functions, the complex analytic functions. But what about arbitrary surfaces? How can you make sense of complex analytic functions there? So Riemann surfaces are those surfaces on which you can make sense of holomorphic functions or complex analytic functions. That's a rough way to think about it. And the converse of this above statement is also true, which means that any compact Riemann surface can be embedded into a projective space as a Zariski closed subset of a projective space, which means it will be expressed as a zero set of a homogeneous polynomial. And so what we can say that Riemann surfaces and non-singular projective curves in P2 are one and the same for us. Yeah, how we define genus is the number of holes in that surface. So now when I tell you that C is a curve, the first thing that, because we can't imagine things in 4 dimensions, the first thing that comes in our mind is a curve like this, right? This is what looks like a curve to us. But I'm talking about complex curves, which means they are in P2, CP2, which means they are Riemann surfaces. They are not actually one-dimensional objects. They are two-dimensional objects, two real dimensional objects. So a complex curve schematically will look like something like this. It will be a surface. It might have some genus. It might not have some genus. It could also be just the sphere, for example. But it will be a surface, not a one-dimensional object. It will be a two-dimensional object. That's what's important to understand. And the number of holes in that surface will be what is known as the genus of that surface. Okay, these are the holes. So, for example, this one is a genus 2 surface. This one is a genus 0 surface. Okay. All right. So, and you might define genus to be half of the dimension of half of the first Petty number, but you don't have to worry about those technicalities. All right, so now that we have defined the notion of curve, we will also define the notion of isomorphism of curves, or a sense of equivalence between curves. And the way we do that is that, so you have C and C prime, they have two smooth projective curves. Since they are smooth projective, yeah, please. It is known as a double torus. Yeah, that is true. Yeah. So this is what is known as a torus, for example. It's a genus 1 surface, and what you're saying, yeah, that is the double torus. Right. Right. So so if you have two smooth projective curves in P2, they are nothing but Riemann surfaces. And so a sense of isomorphism is nothing but a biholomorphism of Riemann surfaces. What is a biholomorphism? It is a holomorphic map which is bijective, and whose inverse is also holomorphism. Since we are on Riemann surfaces, we can make sense of holomorphic maps, as I previously stated, and holomorphic or complex analytic, whichever language you like to use. And biholomorphism is basically isomorphism in the category of Riemann surfaces. Isomorphism of topological spaces is a homeomorphism. Isomorphism of smooth objects like smooth manifolds is a diffeomorphism. Similarly, isomorphism of Riemann surfaces is a biholomorphism. And so now we're in a position to define a very important pair of our story, which is the space which parameterizes all algebraic curves of P2 of a specified genus up to isomorphism. Okay. So this is known as a moduli space of curves. What is it? So the moduli space of genus G curves with n marked points. So please bear with me. It's a bit of an abstract definition, but I'll get to concrete examples in a moment. So a moduli space of genus G curves with n marked points is this following space. You have a you consider the space of all tuples where C is a smooth projective curve of genus G in P2, and you have n points on C which are distinct from each other, which are pairwise distinct. So you cannot have you have to pick n points which are not the same, then pairwise distinct points, and you consider the space of all such tuples such that there is a forget the equivalence one. First think of the space of all curves with all those marked points such that the marked points are distinct. Okay, but this is not quite the space we're looking at. We are looking at a space modulo certain isomorphism, which is that two curves or two tuples C P1 up to P1 and C prime Q1 up to Qn, they are equivalent if and only if there exists an isomorphism. What is an isomorphism? A biholomorphism between C and C prime says that phi, this map phi, takes each marked point to the marked point in the other curve in ordered way. So P1 will go to Q1, P2 will go to Q2, and so on. Pn will go to Qn. Not that P1 will go to Q2. That is not what you want. Okay, and under this under this equivalence, you consider the class of all equivalence, space of all equivalence classes of these kind of objects. Then what you get is known as the moduli space of genus G curves with n marked points. Okay. The first important question that you can ask is: are these spaces manifolds, or are these smooth, or are they? Do they have bad singularities? What do they look like as a space? The moduli space itself, not the individual objects of the moduli space, but the moduli space itself. So turns out that they are not manifolds. They're not that good, but they are all not that bad either. They are the next best thing that you can expect, which is they are orbifolds. So orbifolds are basically, so manifolds are locally modeled on Rn or some Euclidean space. Orbifolds are locally modeled on Rn modulo some action of a finite group. So if you don't quite understand that, it's okay. I mean, it's a good object. It's not the best object that you can expect, but it's okay. It's an okay object. And there are lots of ways of seeing this. One way is looking at MGN as the quotient of the Teichmuller space by the mapping class group. Please ignore that if you don't know what those things are. Okay. So there is one thing. The next important thing one can ask is this moduli space compact under certain meaningful topology? And the answer is not really. It is, so these spaces are not generally compact. And why do we care for compactness? Because compactness is a very key feature in intersection theory, because intersection theory deals with understanding intersections of submanifolds of manifolds or subvarieties of varieties, and the enumerative geometry deals with the most famous way of answering questions in enumerative geometry is first to construct this moduli space, which is space parameterizing all the objects which you want to count, and then you do intersection theory on it, which is you apply constraints on it, the constraints that you want, such that ultimately what you get is a zero-dimensional object. But a zero-dimensional object need not be a finite set of points, but a compact zero-dimensional object will be a finite set of points. So then you can expect it to count it, right? So what you need is a compact moduli space, not a non-compact moduli space. There is no point in doing intersection theory on non-compact spaces, because after, if you reduce the dimension to 0, you might not get a finite set of points. So it doesn't make sense to count that. So why is this moduli space not generally compact? So I'll just give you one example of a sequence of curves that is not does not converge to a curve. So by the way, compactness can be described in many ways. One of the ways is that any sequence in the linear space should have a converging subsequence. I hope this is something that you guys know. So one example of such a sequence in this case is, so you consider this sequence of curves, which is the zero set of xy minus z squared by n. So this is the sequence. And if you think of just the open part of this thing, I mean, as you see, this is a complex curve. The real part of it will be, if you take a chart, suppose z not equal to 0 and you put z equal to 1 there, then what you will get is the zero set of xy minus 1 by n, which would look something like this. It will be a hyperbola, right? But now if n tends to infinity, well, okay, I'm not defining the topology yet, but in a quote unquote sense, then xy, this will converge to, so xy equal to 1 by n will go to xy equals 0, right, in a quote unquote sense. So what is xy equal to 0? Xy equal to 0 is the union of these two lines, right? Just the x and y axis. And it makes sense. Right? So this is how the sequence will look like. This will keep going, this will keep going, and so on, and it'll kind of converge towards the pair of lines. And this is, of course, not a smooth object, because this point is a singular point. On this point, you cannot have a smooth chart. So which means your sequence of smooth objects is converging to a singular object. So there is a nodal degeneration. This is what known as degeneration. And this is a nodal point. So this is what is known as a nodal degeneration. But anyway, this is an example of why, or an example to show or illustrate rather why these spaces are not generally compact. And the best thing that we can do next is to add those objects that are in the sequence. So this nodal curves that we are getting as limit of these smooth curves, let us just add them to the space. And then we construct the space which consists of all these new type of objects, which now are not just smooth, but we allowing them to be nodal. Then we can expect to maybe get a compact space. And this is a famous result by Deligne and Mumford. I forget, I think in the 1990s or something, which is known as the Deligne-Mumford compactification of MGN. And they give a meaningful topology to it. And they add these objects which are now known as stable curves. I'll define what these things are. And under certain topology, this becomes a compact space. Okay, now this is interesting because now we can do intersection. Okay, I now here define what a nodal point is. I won't go into it. I have more or less described what a nodal point is. This is it's a way of writing the equations for a nodal point. Ignore that. Okay, next, let's come to the objects of this new compactified space that we're talking about. So these are known as stable curves. So before going to a stable curve, let's first define what a pre-stable curve is. A pre-stable curve in P2 is a tuple C x1 up to xn with n marked points, such that the curve is at first nodal singularity. So now we are allowing for nodal singularities. Your curves could be smooth, but your curves could also be nodal. But this is it. We can't go beyond that. We won't ask for cuspidal singularities or higher triple point, or I don't know, higher singularities. We won't worry about. We won't consider those. We only allow curves at first which have at first nodal singularities, and which have marked points which are not nodal. So these marked points should not be the nodes of that curve. Okay, and a pre-stable curve is said to be stable if each rational component, meaning each genus 0 component of it, has at least 3 special points. I'll tell you what a special point is. And each elliptic component, meaning each genus 1 component, is required to have at least 1 special point. And the special point is defined to be a marked point or a node. This is the example of. Oh, sorry. Can you hear me now? Okay. So where did you lose me? Should I repeat the definition? All right. All right. So what I was saying is, pre-stable curve is said to be stable if each genus zero component is required to have at least 3 special points on it, and each genus one component has at least 1 special point on it. And a special point is defined to be a marked point or a node. And there is no restriction on higher genus components. I'll tell you the motivation behind this definition in a moment, but first make sure that you understand this definition. So this definition might seem abstract. Just look at this picture. This is the example of a stable curve. So look at the genus one, sorry, look at the genus one component. So this the thing which is of one whole. This has how many special points? There is one node point. So these where the points where these curves come together. Okay, let me just draw this. Maybe that would make sense. So the points where this curves. So this is genus one component. You add up rational component to it, which is a genus zero component. This is a nodal point because the curves are uh, well, the curves are glued together here. This is not a smooth point because you cannot draw a holomorphic or a smooth chart around it. And you have suppose a genus two component here, and you have a genus zero component again. Then notice automatically that this genus one component has 3 special points. This one. So this is fine because we need at least 1 special point. But notice that this genus zero component has only 1 special point, this nodal point. This is not yet a stable curve. We need to add 2 more special points to make it a stable curve because it needs at least 3 special points. You can of course add more than that. That is fine. That this also is a special stable component. Sorry, this is also a rational curve, rational component with 5 special points. This is fine. We need at least 3. And this genus zero component, sorry, genus two component has 1 special point, but we don't really care because we don't have any restrictions on those. So these are the curves. These are the kind of curves we are looking at. These are not smooth anymore because you have these points which are they are not smooth. They are nodal points, and but this is we have to allow for those to make the space compact. That's the point. All right. So this is an example of a stable curve. This is an example of a stable rational curve with a self node. I'm not going to that. And when you the motivation behind the definition of this stability is that if you have this condition, this is equivalent to saying that the automorphism group of this curve is actually finite, and that is required for technical conditions. I'll not go more into that. But anyway, we are now in a position to define the compactification of MGN, which is just you add the stable curves to your point, to your original moduli space. You add these new kind of objects that we're not talking about, which are allowed to have nodal singularities. And then under the same sense of isomorphism, this becomes a compact space, and this is known as the Deligne-Mumford compactification of the moduli space of curves. Okay. An important example to keep in mind is the following. The 4-pointed moduli space, so this we'll use in our just after a while in our talk. So the 4-pointed moduli space, meaning it's the space of all genus zero rational genus zero smooth curves with 4 marked points. This can be identified with P1 minus 3 points. We just take these points to be 0, 1, and infinity. And its Deligne-Mumford compactification can be identified with P1. This is not easy. This is not difficult to see because M04 and fine. Is this fine? Right. Sorry. I don't know why this is happening. Let me just check if everything is all right. Okay. Things. Yeah, I'm not sure why this is happening. Are you sure? This is audible, right? Okay, sorry about that. So yeah, what I was saying is that this example is something that you should keep in mind. I've defined MGN in a very abstract way, but the only example that you should keep in mind is M04, which is the space of all genus zero curves with 4 marked points. And I'm saying this can be identified with P1 minus 3 points, which we take to be 0, 1, infinity. And is Jellin-Mumford compactification can be identified with P1. So uh, the closure of P1 minus 0, 1, infinity inside P1 is P1 in some sense. And the proof is not very difficult. We know that any smooth rational algebraic curve is biholomorphic to P1, which is just saying that there is only one genus 0 Riemann surface up to biholomorphism. That is a well-known theorem. It follows from uniformization theorem, for example. And so forget the 4 marked points. If you have just, for example, if you have 0 marked points, then M00 will be just be 1 point because up to isomorphism there is only one rational curve. Okay. What about M03? M03 will also be 1 point because this is a standard fact from complex analysis that given any 3 points, any 3 distinct points in the complex plane or in the projective plane, you can have a unique automorphism or a unique biholomorphism which takes these 3 points to 0, 1, and infinity. So M03 is also just 1 point because up to isomorphism there is only one such uh, point, which is one such curve, which is a P1, 0, 1, and infinity. All right, and so now we have 4 points. So it's not just so M03 will be just 1 point, but M04 will be actually parameterized by the 4th point because the first 3 points now are fixed by automorphism because you can find a unique automorphism which takes it to 0, 1, and infinity. So the 4th point is now only free to move around, and so the 4th point is can move around in entire P1, but it cannot quite move around in entire P1 because the marked points need to be distinct. So it cannot be those 3 points that we're talking about, 0, 1, and infinity. So apart from 0, 1, and infinity, this 3 point can move around. So your M04 can be identified with P1 minus 0, 1, and infinity. And now if you want to look at it in Mumford compactification, then there are only 3 following boundary devices, which I'm representing like this, but which actually look like this. So I'll tell you what exactly I mean. So you have P1. So a P1 is basically a sphere topologically, and you have 4 marked points on it. 3 of them are fixed because, well, up to isomorphism, it doesn't matter what you take. And the 4th one is free to move. So the 4th one can go anywhere and it parameterizes the entire of P1 modulo these 3 points. But in its compactification, so when it in the limit, this point can actually approach each of these points. This can go here, this can go here, this can go here. In which case there will be nodal degeneration. So if you mark the points 1, 2, 3, 4, there are 3 possible cases. This 4th point can either go to 1, or it can merge to 2, or it can merge to 3, which will result in 3 cases. One is this thing bubbles off like this. So you get 1, 2, 3, 4, or it goes to wait. So this is the case where 4 goes to 3. So this is this case, or in this case where 4 goes to 2, you will have 1, 3, 2, and 4. Sorry, what am I doing? 1, 3, 2, and 4. And in the final case where this thing approaches 1 will be 1, sorry, 4, 2, and 3. Yeah, these are the 3 possible boundary devices. So what is a boundary divisor? Forget the word divisor. These are the boundary terms of here. So you have added new objects to your moduli space to make it compact. These are precisely the 3 new objects. That's it. That's simple to understand. You had the moduli space of genus 0 curves, which is just a P1, but then you also have marked points on it. So okay, you have 4 marked points. 3 of them are fixed by automorphism. The 4th one is free to move. But now, since you're looking at the compactification, so it can degenerate, this point can approach other points as the limit tends to infinity. So you have 3 more new objects that you add to compactify your space, and these are precisely these 3 objects. That's it. That's all you need to know. All right. Okay. So that brings us to the end of the well. half of the first part, which is understanding moduli space of curves. I hope this is okay till now. If you have any questions, please tell me. Otherwise, I'll move on. Exactly. Yeah. One objective is this. And the main idea is to add a few more objects because you are being too restrictive when you define the moduli space of smooth curves, which is why it is not compact because it doesn't have enough number of objects in it. So you have to relax your conditions a little bit. So you allow a bit worse than smooth points. You allow nodal points, and then you can expect that it will be compact. So this is the precise sense in which. Okay, right. So now these are the curves that we want to count. But the problem is it's not easy to directly understand intersection theory on this moduli space. So what was Kontsevich's brilliance was that he did not look at this kind of moduli spaces. I mean, of course, he did look at them, but the main idea came from looking at curves not as curves, but as images of maps. So a curve in P2 can be thought of as in two different ways. It can be thought of as a zero set of a polynomial, that is true, but it can also be thought of as a map from P1 to P2, or as the image of a map from P1 to P2. And that is the next object that we are considering, which is known as the moduli space of holomorphic maps, holomorphic curves, whatever you want to say. You can ignore the word pseudo there, that is because that's, so maybe I should spend 1 or 2 minutes here since, or maybe I'll spend enough in after a few slides. Since some people are interested in physics, I can give you a little bit of connections with other things. But anyway, I'll do that in a few more slides. So ignore the word pseudo for now. Okay, so we now look at a different kind of moduli space. We look at now the space of maps from P1 to P2 as opposed to just curves in P2. Okay, so so this is the exact thing. The way we define degree is that you push forward the fundamental class of P1, and that should be d times the class of a line. If you don't understand that, then it's okay. I'll tell you a very simple way of looking at degree d curves in P1 to P2. So what we are looking at is curves from P1 to P2. And a curve from P1 to P2, since these are projective spaces, it's easy to describe them. So this will look like something like this. So a curve in P1 will have x and y two coordinates, and this will go to somewhere u1 of xy, u2 of xy, and u3 of xy, where u1, u2, u3 are degree d polynomials, homogeneous polynomials. That is exactly what a holomorphic map from P1 to P2 looks like. That is a theorem in itself, but for now you can just think of holomorphic maps like this. I hope this is clear. I mean, these are just so P2 will have 3 coordinates, so P1 will have 2 coordinates. So this map is well defined in some sense, and these maps and these coordinate functions are basically just polynomials in x and y. So this is how a curve looks like. Anyway, so right. So, but if I say that these are the objects that we want to count, I would be slightly wrong because we are interested in the image of this curve as opposed to we are interested in the image of this map as opposed to the map itself. So we need to mod out by an equivalence. So let me explain that a bit more. So suppose we want to understand this circle. So forget all complex things, just look at the real plane. Suppose you consider this circle, right? Sorry. Yeah, so this is a circle in R2. We want to look at its parameterization. So we want to understand, so this is a one-dimensional object. We want to understand it as a map from R1 to R2. So this is a subset of R2, but we want to look at it as a map from R1 to R2. So how do we do that? One easy way is, of course, you send t to sine t and cos t. Then you will get the circle. As t varies over, well, I should actually write 0 to 2 pi, but I think you understand what I'm trying to say. And okay, this is one way to do that. But what if I do this? We can also do t goes to sine t square cos t square. This is also a parameterization of circle. So the image of both of these maps, so this is u1, say, this is u2. both of these maps are the same image. We don't want to count this separately because they are, well, they are the same objects that we are interested in actually. We are not interested in the maps, we're interested in the images of the maps. So we need to, so up to a reparameterization of the domain. So T going to T square is a homeomorphism of the domain. So up to a reparameterization of the domain, these maps will be considered the same because we are interested in the image, not the map, right? So what we do is we define an equivalence between two maps, between two degree T maps, and we say that U1 is equivalent to U2 if and only if there is a automorphism in of P1, which is just a biholomorphism from P1 to P1, such that U2 is U1 composed phi, which means that, so just come back to this again. Previous case, you have U1 from P1 to P2, you have U2 from P1 to P2, and I'm saying U1 is equivalent to U2 if there exists phi from P1 to P1, which is an, sorry, P1 to P1, which is an automorphism, such that, so you have U1 from P1 to P2, and you have phi U1, and you have, this is U1, this is U2, this is P1. Wait, am I making things confusing? Yes, this is U2, this is phi. This is the diagram that you should keep in mind. This diagram should commute, which means that U2 should be equal to U1 composed phi. This is all we want, because up to reparameterization of the domain, we don't care about what those maps, we don't care if the maps are different. So under this equivalence, we define the following moduli space, which is that you consider the space of all holomorphic maps from P1 to P2. They should be of degree D. I already explained what degree D is in a more humble sense, and such that the points are distinct. Modulo this equivalence that any two curves are related by an automorphism of the domain in this sense, and the marked points are related in this sense. This yi equal to phi inverse of xi. I'll tell you why that is important in a while. I'm running out of time a bit, so I'll go a bit faster. Right. So, so two important questions that we previously asked and we will also ask now are as follows: is this space a manifold? Well, answer is it is almost a manifold if you remove certain problematic maps, which are known as multiply covered maps. And this manifold is what one gets is of dimension 3D minus 1 plus n, which is basically that number of generic points I was talking about. This is the dimension of that moduli space. You need to cut down by that dimension to actually hope to get a finite number. Next question you can ask is this space compact? And the answer is again, no, need not be. And to do intersection theory on this, we need to compactify this space. By the way, why is this space not compact? You can take the same example, by the way. The example that I gave here. Where was it? Yeah, this example. So here I talked about the curve itself. You can parameterize this curve in a, so maybe you can do this. You can take this sequence of maps which sends xy to let's see, x square, y square, I think n squared, z square, sorry, nz or z by n. Yeah, this is the one. If you look at the image of this sequence of maps, this will be the same images as that, and the same argument will work that if you send it to a degeneration, then this need not be a smooth curve anymore. So what you need to do is you need to add more points to it, so that, or more objects to it, so that you can compactify the space. But again, these are now maps. These are not. This is the same arguments won't work. You need to work more. So there are two ways of looking at things here. Mm-hmm. Yeah. Oh, sorry, I am wrong here. One second. This square should not be xy should be equal to z square by n square, right? Yeah. Sorry. This is the map, I think. I mean, yeah, you understand what I'm saying, right? You parameterize the curve and you get an appropriate map. That's the idea. Okay. So there are lots of ways of looking at this. There are two kinds of mathematical communities working in Gromov-Witten theory. One is on the symplectic side, one is on the algebraic side. Symplectic geometers, I am a bit more biased towards that. So the theorem that is proved in symplectic topology, which is due to Mikhail Gromov, this is known as the Gromov compactness theorem. And Mikhail Gromov's original motivation was not to do enumerative geometry actually. His motivation was to create certain invariants for symplectic manifolds. Symplectic manifolds are a problematic set of manifolds because they don't have any local invariants. So there is something known as the Darbo's theorem, which says that any symplectic manifold locally, all symplectic manifold locally looks the same. So there is no such notion of curvature that you get in Riemannian geometry, for example. So that hence the name symplectic topology, as opposed. So you don't look at local things, you want to look at global things because locally all symplectic manifolds look the same. They are not interesting. So creating invariants of symplectic manifolds is therefore a very important way of looking at symplectic manifolds, because then globally you can distinguish them from each other. And Gromov's idea was that you look at maps from a Riemann surface to a symplectic manifold, and they are known as J-holomorphic or pseudo-holomorphic curves because symplectic manifolds need to not have a holomorphic structure on it. So they choose an almost complex structure. If you don't understand what I'm saying, just ignore. I'm just giving you some trivia facts. And these are known as J-holomorphic maps from a Riemann surface to a symplectic manifold. And one can then define and also hopefully compute what are known as Gromov-Witten invariants. So what you do is you basically count pseudo-holomorphic curves in a symplectic manifold, passing through appropriate number of generic points, and that number turns out to be an invariant, a symplectic invariant of that symplectic manifold. And the interesting part that I think if people in physics are interested in, then this has got very interesting connections to theoretical physics, especially string theory, or more particularly topological string theory. So as you can see, this name is Gromov-Witten theory, whereas this paper, you would think that Gromov and Witten have written a paper together and this came out to be like that. That's not how it happened. Gromov had a paper in 19... Yeah. So Mikhail Gromov had a different paper altogether for symplectic manifolds. He actually did not define Gromov-Witten invariants in the way that it's defined now. It later on came to be that way because Edward Witten, the famous mathematical theoretical physicist, he then looked at its applications in topological string theory. So in string theory, I think you look at maps from Riemann surfaces to certain manifolds, because I think you consider your objects. So I'm not knowledgeable in this. It's just what I vaguely understand. You have so in string theory you look at strings as your fundamental objects, and those strings form what is known as a world sheet, I think, and that world sheet turns out to be in many cases Riemann surfaces. And I think the fundamental way of doing any field theory is that you look at maps from your Riemann surface to your target space, and you want to integrate over those maps. I think those are known as Feynman integrals, and those integrals then those are basically, I think, action integrals, and one then does physics with it, so on and so forth. But in the particular case of a Riemann surface and what is known as a Calabi-Yau manifold, the computation of string theory becomes much easier. I think that is the case what is known as topological string theory. I'm sorry, I might be wrong in certain things. I'm not an expert in this, but this is the general idea, and which is why Gromov-Witten invariants are so are so exciting in theoretical physics as well. But yeah, they are rational numbers. They need not be enumerative. They need not be integers. So, but in our case, we don't have to worry. These are enumerative numbers because of technical reasons. But in higher genus or in other spaces, more exotic spaces, they need not be rational numbers. The main reason is that you have symmetries, you have non-trivial automorphism groups of your curves, which you need to divide out by to actually get the count. And in certain cases, those are actual numbers which you have to divide out by. So what you get is a rational number as opposed to an integer. And yeah, so Gromov-Witten invariants need not be anywhere. That is true. You are counting that, but you're counting it with weights. That's the problem. You are counting it with weights, which weights which come from the symmetries of your curves, and these weights could actually be non-trivial, and they could give you a rational number. That's the point. So it's not actually counting; it's counting with weights. That's where the problem comes in. Anyway, so lots of philosophy. Let's get down to business. So yeah, this is known as the Gromov compactness theorem. There is no way in hell I can prove this right now. It's a huge proof. You can refer to Magdalf Salamon's book on J holomorphicus and symplectic topology. And yeah, so but let us try to understand the compactness statement better, which is that let us try to understand what objects are there in there. So this is known as the moduli space of stable maps. Notice that I'm only defining rational stable maps. I won't go into genus G stable maps. So rational n-pointed stable map consists of a connected marked rational curve, which I have already defined, and a morphism, a holomorphic map from that curve to P2, satisfying the following conditions. So the singularities of that curve can only be nodal. We are only allowing nodal curves. And the distinct marked points on that curve are not nodal. They are distinct, but they're not nodal. And if a component of C, which is rational, which means it's isomorphic to P1 or it's a genus 0, and that map is constant on that component, then that component should have at least 3 special points. So notice that this is a bit different from a stable curve. So a domain of a stable map need not be a stable curve, because if you can have in principle unstable component, as long as your map is non-constant on it, right? And but if you have that the map is constant on a component, then your component needs to be stable. Okay, and the reason again is that you want the automorphism group of your map to be finite and not infinite, and that is an equivalent condition. So if you put all those objects in and you give it a appropriate topology, which is known as the Gromov topology, then what you get is a compact space, and this is in the moduli space of degree D, rational and pointed stable maps into P2. Okay, and from the symplectic side, this is the theorem. This is the Gromov compactness theorem, which is that this space is compact under the Gromov topology. But there is also a equally important, equally exciting field going on, which is from the algebraic geometry side. And I don't understand it very, very well, but they basically do similar things, but in different generalizations. So symplectic geometers want to go into arbitrary symplectic manifold, whereas algebraic geometers want to go into arbitrary algebraic varieties. And so for them, the language, the generalization becomes a bit different. So what they say is that there exists a coarse moduli space, which is compact and which parameterizes the isomorphism classes of these stable degree maps. Okay, and the next important result. So this is one important result that we needed, the compactness, and the next important result that we need is what is known as gluing theorem, which is saying that okay, you have a space M0n and you have a space M0n bar. Okay, M0n bar is compact, but how does M0n sit inside M0n bar? M0n sits inside M0n bar fine, but how does it sit? As in, if you take the closure of M0n inside M0n bar, does it actually equal to M0n bar, or does it equal to something else? I mean, you might say that okay, this is a bar, so it will be the closure of this, but I hope you understand that that's not how we defined. We did not have an ambient space in which we could have defined the closure. We added new extra objects to it. So we cannot assume or we cannot expect that this closure should be actually equal to the new ambient space that we have defined. But it turns out that for the case of genus 0, this is actually true. So the closure of M0n inside M0n bar is actually equal to M0n bar, and M0n sits as an open dense set inside M0n bar. So notice that this is, it might seem, I mean, a very expected statement, but it is not so, I mean, it should not be expected. And the reason is for higher genus it's actually not true. If you take M0 MGN for higher G and you take MGN bar and you take the closure of MGN instead of MGN bar, you will not get MGN bar. In fact, things become very bad when you get to higher genus. It could also be the case that the boundary is so large that its dimension is larger than in ordinary or sorry original moduli space. Uncompactified moduli space is dimension sometimes lower than its entire boundary, which means there is no way in hell that you take the closure you will get the entire space. That did not happen for higher genus. So this is actually an exception to the rule in some sense. This is not something that you would expect, but it does hold in genus 0, so life's easier for us. And so one can now come to the proof of Kontsevich recursion, which is saying that if you denote the number of rational degree D curves in P2 through m points where m is 3D minus 1, then we can have this following recursive relation, which actually computes ND for all D. And notice that I defined this m extra because I just want to keep track of how many points it's going through. If it's not going through 3D minus point, you immediately ask it to be 0 because it doesn't make sense. But if it does go through 3D minus 1 point, then you can apply this formula, and then you can actually, if you give this formula to a Mathematica or some other favorite software, mathematical software, you will get all the numbers that you want. You can try to do that if you want. And okay, so the proof I will not go through my slides. I'll actually do it here. That is easier, I think. I will not go through the entire proof. I won't have time. The idea is as follows. So what you do is you consider. So you have this moduli space of n-pointed degree D rational curves into P2, and you have certain maps into P2, which are known as the evaluation maps. What it does is it takes a element here u comma x1 up to xn, and it evaluates it at the xith position, at the xith mark point. Sorry. And why is this well defined? Because this is an equivalence class of tuples. It could why is it well defined? Why if you choose a different equivalence representative, then why does the thing remain same? That is because the way we had defined the equivalence relation on the moduli space, it ensures that this map is well defined, which is the reason for defining it in that clear way. Okay, these are so I should say u of xi rather, not f of xi. Yeah, this evaluates u on xi, and you have these are you have n evaluation maps. Okay, there is another map from m0n p2d to say m04. I'll take, and this is denoted by pi. This is known as the forgetful map. Not quite. This is more similar to the projection map than that, because you are forgetting. So a projection map does what? You have say P1 cross P1, and you project it to P1, and you just send x comma y to x, right? So you're forgetting the y thing, right? This is exactly what this thing is also doing, because this forgetful map, it's not quite that also, but I mean, in some sense, it's similar. This is not quite similar to that because it's evaluating this on that, right? So the forgetful map is closer to what you're saying, because what it does is if you have a stable map, then you forget the map itself. You just look at the domain curve, right? You have what is a stable map consists of? It consists of a domain curve and points and a map. Forget the map. That's what the forgetful map is doing. Forget this u, right? And but the only problem is that, as I said before, that the domain of a stable map need not be a stable curve, because it could be non-constant of that component, and we won't care about that stability of that component. Which is why one needs to do what is known as a stabilization of that unstable curve, which just means that you contract of the unstable components. So if you have a unstable component attached after you forget the map, just forget it. That's it. And if you have a marked point on it, then just forget the component and keep the marked point. That's it. Okay. So Okay, so the idea is as follows. I told you that M04 bar. So please listen to this carefully. This is the most important part of the entire talk, I think. M04 bar is isomorphic to P1. Okay, and P1 is path connected. This is a well-known fact. P1 is homeomorphic to S2, so it is path connected. Now, any 2 points in P1 would thus determine same cohomology classes. So if you know what that sentence means, it's okay. If you don't know, that is also okay. I won't elaborate on that much, but my main point is, if you take those two, remember that M04 had those three boundary devices. If you consider these two boundary devices, 1, 2, 3, 4, and 1, 3, 2, 4, which are basically these two things, 1, 2, 3, 4, 1, 3, 2, 4, then these two things are, as cohomology classes are equal, or as boundary divisors are equal, because P1 is path connected. That's the most important fact. If you know that cohomology is up to homotopy is it's equivalent, then you would know that if you have a path connected uh, space, then any 2 points will determine the same cohomology classes. How it determines a cohomology class, it's a separate discussion altogether. One can use Poincare duality and everything. But anyway, just for now, just bear with me. If you don't understand what a cohomology class is, just think of it as an algebraic representative of your geometric object that I'm talking about. And turns out that although the geometric objects are not equal, in that algebraic representation, those two things are equal. So 1, 2, 3, 4 is actually equal to 1, 3, 2, 4. Okay. Now what we do is we pull back via this forgetful map. Okay. And this will consist of all. So if you don't understand the star, then just think of it as inverse and the cohomology class compared to that. And if you now the important part is to understand what is in pi inverse of 1, 2, 3, 4 and pi inverse of 1, 3, 2, 4. So what will be in pi inverse of 1, 2, 3, 4? It will consist of all the maps whose domains are whose domain is this. And one is to understand precisely what kind of maps are there in this kind of domains, and that is where your gluing or your gluing theorem comes into picture, which is that these are precisely all the uh, you don't have anything weird, you just have those things because your original moduli space is dense in your new moduli space or compactified moduli space. So what you get is what kind of objects are in pi inverse of 1, 2, 3, 4. Pi inverse of 1, 2, 3, 4 is maps which have the following domain. You have a map U such that on restricted to this component, so this is a map U to P2, and restricted to this component, this is degree D1, and restricted to this component, this is degree D2, such that D1 plus D2 equal to D. This is how a degree D curve in this kind of degree D maps look like. Okay, so now once you have this relation, you can intersect it with the following thing. So you can intersect pi inverse of. So now I think I should go to the slides. So yeah, so we have this thing, we have this forgetful map, we have the relation, we pull them back, and now we consider this cycle. So if you don't understand what this is saying, just think of it in the following way. This second bracket that you have, where you start from F5 star to F3D star, these are basically saying that your curves are constrained to pass through those many number of points, because L is a class of a line in P2, so L square is a class of a point in P2. So and F star means you are looking at the pullback of via your evaluation map. So evaluation, if you pull back by evaluation map, that means that you are considering all the maps which evaluate to that point, which means that pass through that point, whose image pass through that point. So if you intersect all this kind of sub varieties, then what you get is a cycle which consists of, or if you intersect the cycle with your variety, then you will get the class of curves which pass through these number of points. Okay, but we do something different. We don't do all the points. We don't make it pass through all the 3D minus 1 points. We keep these points, okay, but we also make it pass through the first 4 points. We make it pass through this special kind of combination, which is we make the first point pass through a point, the second point pass through a point, the third point pass through a line, and the fourth point pass through a line. I'll show you the image. This is the image. You are looking at maps from this special domain to P2. The first component has degree D1, the second component is degree D2, and the first mark point goes to a point. The second mark point also goes to a point. The third mark point goes to a line. The fourth mark point goes to a line. Okay. This is the way we are looking at. Now, if you actually compute this intersection, so if you compute the intersection of Z with your left hand side, then what I will not go through the entire thing because I won't have time. What you will get is this combinatorial object. You will get a number because I'm appropriately adjusting the dimension so that everything adds to the dimension of the ambient space, and so actually computing them will require some simple combinatorial arguments. But what you will get is this combinatorial number, and you can do the same thing in the right hand side. In the right hand side, what will happen is you have degree D1, degree D2, and you have that the first mark point goes to a point. Now the third mark points and the second mark point switch positions. So the third mark point now will go to a line. The second mark point will go to again a point, and the fourth mark point will go to a line. And again, you do the intersection theory. Then what you get is this number. And if you now, I said that LHS was equal to RHS. Now you bring one component, one term from LHS to RHS, and what you get is this huge equation. And that's basically what Kontsevich's recursion is. So the main important point, these are all combinatorial arguments. The main important point is this equality, and then when you intersect it with Z. So the main important equality is this. This is what is known as the WDVV equation in an appropriate sense. If you don't know what that is, ignore that. But this is what is, I think, relevant in physics also. You will say this is equality of two numbers. How is it a partial differential equation? Well, if you encode these numbers as a generating function and you put it as an ansatz in your partial differential equation, then the partial differential equation will actually give you this recursion. So this recursion and that partial differential equation are one and the same. So this is what is known as a WDVV equation. Okay, I spent a lot of time. I hope Kontsevich's recursion is somewhat clear. I have I think 6 minutes. I'll quickly try to tell you what our work was. This was the proof given by Kontsevich, correct? Sorry? No. Mirzakhani gave proof of Witten's conjecture. That is a different thing. I mean, it could be derived from, I am not sure if it, but immediately I don't see why those two things are the same. Okay, so yeah, so our work was about counting rational curves with an M-fold singular point. I'll try to go through this fast. For the sake of simplicity, consider the case of M equal to 3, which means we are counting rational curves with a triple point. Okay. We simplify the question further. We are now looking at rational curves, degree D curves having a triple point at a fixed point. So earlier we said that the triple point could be anywhere. I mean, curves with a triple point anywhere. But now we are saying, okay, we want the triple point to be at a very fixed point. Okay, which would this is a different question, but let's first answer this question. Okay, the non-trivial claim that we make is the following: counting rational degree D curves in P2 having a triple point at a fixed point and passing through appropriate number of points is the same as counting rational curves in P2 blown up at a point representing that particular homology class DL minus 3, where L is the class of a line and E is the exceptional divisor. So if you don't know what blow up is and what exceptional divisors are, I'm sorry. These are some kind of geometric object. I'll actually get to it in a moment. I'll tell you how to think about it. And all one needs to do is compute the Gromov-Witten invariants of this new space, which is the P2 blown up at a point. This will be the same. So this problem of counting rational curves with a triple point at a fixed point is basically solved because this was done by Gotche and Panthari Pandey. Now, I am saying this is not what we want. because we wanted the triple point to be anywhere in the curve, not at a fixed point. So what we do is, okay, before doing that, we first try to understand the correspondence of it. So this is the correspondence. So if you have a, so this is your, the right hand side is your triple point, as I had previously showed. This is a curve with a triple point. If you blow it up, then you will get something like this. So I'll tell you in a more, this is the picture that you have should have in mind. This is a double point, not a triple point. This is a node. And if you blow it up, what it does is it it kind of extends the curve. It kind of tears of the singularity, so that your now your curve which intersected at the same point two times now intersects this exceptional divisor. This line, the straight line that you see is called the exceptional divisor. This curve cuts it at two distinct points as opposed to the same point on the the plane. So you see this image, right? You have this curve and you want to understand the singularity. What you do is you stretch this curve so that the singularity is now expressed as how many times the curve is cutting this line. So if it's a double point, it will cut this line two times. If it's a triple point, it will cut this line three times, and so on and so forth. Okay, and so instead of counting curves like this, which have singularities, we'll instead count curves which are like this, which are in a different space, which is in the blow up. But now we are dealing with smooth curves. We don't have to deal with singular curves. Now that's the idea that we had. That's the most important idea that we had. Don't count curves as curves with singularities. Count curves with as smooth curves, but in a different space altogether. And but the point is, this answering this question is answering a different question, because the triple point is at a fixed point. So what we do is we allow the fixed point to vary in a, so we allow the triple point to vary in a family. So instead of looking at P2 blown up at a point, we look at a fiber bundle over there, which means we look at, so I'll tell you what exactly we do. So we allow the triple point to vary in a family, which means that we consider a fiber bundle over CP2, whose each fiber at each point is the moduli space of stable maps into CP2 blown up at that point, representing that class DL minus 3. I hope I'm making sense. So at each point, we are considering this new moduli space that we had talked about before. This one, the moduli space where the maps are into a blow up of P2. But now we are looking at the space of all such moduli spaces, and where this point P is varying in over P2. So now if you do intersection, so this is the new moduli space that we have created. This is not the usual moduli space that people generally deal with. This is a fiber bundle version of the moduli space. And now if you do intersection theory on it, now you should get the answers that you want, because now, okay, you are also counting curves with triple points, but you're also allowing the triple point to vary anywhere in the family, which means your triple point could be anywhere, which means we're answering the original question, which is that counting curve, we're counting curves, rational curves, with the triple point, which could be anywhere in the curve. And then one has to do intersection theory in this moduli space. And how do you do that? The exact same way as I talked about Kontsevich recursion. You look at M04 bar, you have the divisible equality 1, 2, 3, 4 equal to 1, 3, 2, 4. Now you pull back to this new moduli space that we have defined, and then again do the, I mean, of course, one has to take care of technicalities and everything, but that's the main idea. You again intersect it with appropriate cycles, and then you get the recursion. And so I won't go into the details of how exactly you do that. And but the main thing that I want to show is that given this kind of definitions, you get this formula. Notice this is structurally very similar to Kontsevich's recursion, and also conceptually very similar. The clever part was to, which was Ritwik's idea, which was to view these curves in a different way. A, this was already known, but B, allowing this singular point to vary in a family, so that you can consider curves with not just triple point at a fixed point, but at any point in the curve. And you construct a new moduli space and then do an intersection theory on that. Then what you get is the expected numbers that you want. So for m equal to 3, this was already done. So we checked and we got all the expected numbers. For higher m, there was no as such direct result. We did some verification that we could, but that those things worked out. And for higher m, of course, there are no results, so we can't verify that. But for m equal to 3, we have done that. So yeah, that's basically it. Should I take one more minute. I just wanted to tell about what future generation directions we are thinking of going. There are lots of thank you. So there are lots of directions that one can go from here, but the two immediate ones is key. Can you extend it to Pn now? Can you look at curves in Pn as opposed to just P2 and enumerate all rational curves then a full point? It should be, I mean, I believe it should be very doable. I was actually thinking of doing it last semester, but I didn't get quite the time. I just need to get used to, I'm still not very comfortable with Gromov-Witten invariants of higher Pn. Once I get comfortable with that, I think it's quite possible to do that. Of course, there are technical things that one needs to take into care, but yeah. What is more interesting and what is conceptually more difficult is, can you now extend it to genus 1 curves? Can you count elliptic curves, that is genus 1 curves with an M4 point in P2 and maybe also in Pn? And the idea would be to use Getzler's solution. So we had this divisorial equality like in M1, 2, 3, 4 equal to 1, 3, 2, 4. In higher genus, in M1, 4, for in higher genus, you don't have a general divisorial equality like this. So in G4 bar, you won't have a divisorial equality like that. But in certain cases, there are. So for example, in M14 bar, Ezra Getzler had given a relation a few years back. It was not as simple as that. It was more complicated than that. But he had given a relation, and one can try to pull that back and then try to see if you can get something for elliptic curves. So yeah, that's basically it. I think I took a bit more time than was expected, and these are some of the references. Please ask me questions if you have any, and thank you so much for your time. Yeah, right. Yeah, yeah. That's very well put. Yes. Mm-hmm. I see. I'll have a look at it. Okay. This how recent is this? Uh, oh, quite recent then. Okay. Okay. Thank you. I'll have a look at it. Okay. So thank you. Any questions? Yeah. Okay. Right. Thank you so much. Thank you so much.